you?
No. Yeah, so this is Asher. He's visiting from Fermilab, where he recently just started. And he's going to tell us about some new ways of detecting high frequency gravitation.
Okay, thanks. Hi, everybody. It's great to be here. I'm going to be telling you about some work from a little over a year ago, as well as something that I usually don't do this. I honestly think it's going to come out in a couple days regarding how to look for exotic, very high frequency gravitational waves using small scale detectors, using methods regarding and signals related to how gravitational waves may either directly or indirectly couple to electromagnetic systems. So let me just get started. In principle, the frequency of a gravitational wave can be anywhere in priority. Famously, we've detected gravitational waves in roughly the hertz to 10 kilohertz band. That's by LIGO and Virgo, and this is going to be further probed by future ground-based and underground interferometers. And in looking further into the future, we're going to probe a large range of low frequencies, for instance, by atomic interferometers. Just one example shown here, space-based interferometers, pulsar timing arrays, all the way down to a nanohertz. And there's really good reason to have so much activity down at these lower frequencies, and this is because this is where astrophysics typically lives. So, for instance, any known astrophysics is essentially bounded to give gravitational wave signals below roughly 10 kilohertz. This is derived from the statement that if you consider two orbiting bodies, the highest frequency that the system is going to emit typically is when they're moving relativistically, roughly a Schwarzschild radius apart from each other. And if these are dense systems comparable or much heavier than the mass of our sun, this corresponds to frequencies below 10 kilohertz. So as a result, if you're interested, like I am, in talking about high frequency gravitational waves, in some sense, by definition, if they're detectable, you're talking about looking for signals of new physics. Now, often what's discussed within the context of new physics sources of high frequency gravitational waves is probing the early universe. This is because if you have some event, say some large phase transition that shed a lot of energy at very early times, the wavelength of those gravitational waves are bounded by causality to be smaller than the Hubble radius at that. It was smaller earlier on. So for instance, if there were some events that created gravitational waves filling the entire universe, when the temperature of the universe was heavier than roughly 10 to the 11 GeV, that would give rise to gravitational waves today when you redshift these things down to gravitational waves roughly heavier than 10 kilohertz. So it's often discussed as, we're up here because we're looking for stochastic gravitational wave radiation from the very early universe. However, that's a little misleading. I think a more honest perspective is actually that's not why people should be interested. And the reason is because if you, let's say you normalize the strain, dimensionless amplitude of these gravitational waves by h, and you characterize it by a power spectrum. So this is the power of these gravitational waves per the frequency. I'm normalizing it here to be something that's possibly within the realm of being detectable. And here I'm asking how much energy density there is in these gravitational waves compared to all the energy density in the universe. At high frequencies, this grows quite rapidly. So what you find is fixing the strain to be detectable, maybe at frequencies above a kilohertz, this would overclose the universe and extra radiation density.
This is just comparing not just to an effective, but the total and
The critical energy.
so it's
So like
being generous being generous to new physics.
Yeah. Right. I just don't want to. I want to remain in the flat universe per se.
Right.
The bound is, substantially stronger by few orders of magnitude, compatible with CMB or BDN. But the statement is, as soon as you start fixing the strain to be detectable, let's say, and scaling the frequency to be above a kilohertz, this is not cosmologically viable in the most conservative sense. So this is somewhat of a misleading statement, the fact that you're kind of probing these high frequency primordial gravitational waves. This is, of course, very interesting at lower frequencies, but at higher frequencies, not so much. My own personal perspective of why you should be interested in this range up here is that we have no idea what's up there. And as I'll be telling you about today, there's a lot of opportunity to use small detectors, existing detectors, or maybe just even existing data. So just reanalyzing existing data. And because this is so easy to do, we have no idea what's up there. There might be something unexpected. Why not do it? And as I'll mention very briefly towards the end here, there are other new physics scenarios that might give rise to not high frequency gravitational waves filling the universe, but more local late time sorts of gravitational waves at high frequencies that could in principle be detected. Okay. Now, one question you might have about that is, do we really need a new technology? The sensitivity of existing detectors like LIGO is quite great, peaks in sensitivity at around 100 hertz or so, and it's kind of tapering off here due to the fact that these interferometers are becoming limited by shot noise at high frequency. The wavelength of the gravitational wave is becoming small compared to the arm length. But naively, you would think, well, can I just think about scaling this up? Of course, it's being diminished quite rapidly, but this still represents very small signals. Can I do this? If you talk to experimentalists on LIGO or Virgo, the answer is no. The cutoff usually shown at 10 kilohertz or so is a human-made decision, but the reason to do that is because the transfer function, namely how if you want to translate a high-frequency gravitational wave to a high-frequency observable, the transfer function becomes incredibly complicated, as shown here. This kind of forest of resonances at high frequencies, and there's a lack of a feasible way, at least the people on these collaborations currently know how to do to calibrate their optical response at high frequencies. So the basic statement is that it's probably not going to happen anytime soon, maybe in the future, that these interferometers will be able to extrapolate their reach to very high frequencies. So what I'm going to be telling you about today is, in fact, how we can use new technology to probe this kind of parameter space up here for frequencies ranging from roughly 10 kilohertz all the way up to gigahertz using detectors roughly this big. So that's the quick introduction, the quick pitch. The rest of this is sectioned off into 3 different groups. I'll be telling you how a GR plays with electromagnetism, how are Maxwell's equations modified when you have a gravitational wave washing over you. With that understanding, we'll talk about how to hijack existing dark matter experiments. So for instance, small experiments used to look for so-called axion wave-like dark matter, and how those things can just be reanalyzed, that data can be reanalyzed to look for very high frequency gravitational waves, and narrowly centered around the gigahertz of frequency. And finally, I'll be telling you how we can revive some previous experiments, something that I'm going to rebrand and call as a Weber cavity, analogous to a Weber bar. Familiar with that, to look for a much wider range. But that's the rest of this talk. Are there any questions or comments about the introduction that I made so far? Okay. So the first thing is based on this work from a little over a year ago. And the starting point is how to think about electromagnetism coupled to GR. So we're used to thinking about Maxwell's equations as just being derived from F mu nu, where this is contracted with just the flat space metric. More generally, this is sitting inside of an axion where the metric is non-trivial. Okay, so the starting point is to take this metric and expand it around a linear order, expand it around flat space for linear order and strain tensor H. When you do that, what we find is that the order H piece of this action looks like a current coupled to the vector potential of electromagnetism. Here, I'm borrowing the terminology of the axion community, an effective current. It's not really a motion of charges or anything, but it will source electromagnetic fields just like a current will. So it enters Maxwell's equations like a current does. And it's non-zero if there's some gravitational wave present in the form of H, and some background electromagnetic field present in the form of the field strength. Now, this has been known about for decades. It's known as an inverse Hertzenstein effect. Okay, and it's basically the statement that in a background electromagnetic field, a gravitational wave passing by will convert into a signal electromagnetic field, or a graviton will convert into a photon. Okay, this has been known about for a long time, but what we found when we started investigating these things is, in fact, the signal was never really properly described because there are a lot of kind of gauge artifacts hanging around improperly. I'm going to go into this more in a more detailed way, but quickly, the reason that there's an error, or the basic error that everyone was making regarding these kinds of signals, was the fact that you need to be careful about what frame you're working. And you might be tempted to not worry about this because typically in linearized GR, where you expand the linear order and strain, an order H tensor that transforms covariantly is approximately invariant to linear order and strain. So for instance, the Riemann tensor there's an order H tensor. This gets corrections between gauges or between frames in linear SGR up to order H squared. So you usually don't worry about that. And you might be tempted to say, oh, okay, this looks like a vector. But the important point is that this is just some order H piece of a bunch of order one thing that I defined. It's order H correction to an order one action. It doesn't transform covariantly between gauges, neither does the metric. So these things are not invariant in linear SGR. Sorry, neither does the strain metric does, but neither does the strain. So you need to be careful about how you treat what your coordinate choice or your gauge choice in GR. And I'm going to now tell you some more details about that. So in GR, you're probably familiar with the idea of diffeomorphism invariance. So you're allowed to redefine your coordinates and the physics doesn't change. In linearized GR, you're restricted to a subset of that gauge freedom. Namely, you can relabel your coordinates goes to x prime that are just shifted. For one example of that is where it's just shifted by some function c mu. And provided that the derivatives of c mu are small at the level of order H, this is a symmetry of linearized theory of linearized GR. This represents some gauge freedom, but it's not just a mathy thing. It's really just, it's thinking about what frame of reference I'm going with. Okay, so really these different choices of gauges are different frames of reference. And they might sound like a small effect. These are only order H corrections to the physics, but the physics, the leading order that I'm interested in is order H. That's any kind of signal from the gravitational wave is order H. So this represents an order one relative correction to any kind of effect that I'm worried about. So it's definitely important in how you think about investigating these kinds of signals. Okay, so if you open up any standard textbook like Misner, Thorne, or Wheeler, and or other textbooks, what you'll find is that there are two main choice of coordinates or two frames that people talk about. By far, the most popular choice is the so-called transverse traceless frame, or the TT frame. Okay, and the reason for this, as I'll show you, is that the metric is especially simple. Most of the entries are zero. And so it's by far the more popular choice. It simplifies the algebra, makes the math a lot easier. And as I'll discuss, it actually kind of confuses a lot of the physics. It can kind of get tripped up quite easily. The more intuitive frame is the so-called detector frame. It's the frame of the Newtonian observer. This is something that approximately generalizes the idea of a local inertial frame to a timelike geodesic. Okay, it's things reduced to flat space, Minkowski metric in the limit that you would think they would. It's intuitively the more simple frame, but mathematically it's much more complicated. The metric looks a much messier, so people typically use this and don't use this. So let me go through that. So the TT frame, the stress tensor is shown, or the strain tensor is shown here. The gravitational wave looks like a plane wave, in this case traveling in the z direction with frequency omega g, and most of the entries are zero. Okay, where these things just tell you the relative polarization, either the so-called cross or a plus polarization of the gravitational wave. Now, this looks like just some random choice of coordinates. What does it mean physically? Physically, this is the frame where freely falling masses that are initially at rest before a gravitational wave arrives remain at rest while the gravitational wave is washing over. Okay, so the coordinates are in some sense defined by these free test masses. So in some sense, you have a free test mass and the gravitational wave washes over you and you wiggle your head in the right way such that it looks like its coordinate position is changing. There's nothing weird about that. Coordinates are physical, but how you essentially define your coordinates. And as a result, the effects are very subtle. So something that's not a free test mass, a very rigid object held together by intermolecular forces, you can make very, very rigid, you think, by taking the first acoustic resonance of that system and have it be very, very high compared to the frequency of gravity. That's something that you would imagine to be a rigid ruler, someone whose first acoustic vibrational mode is at a very high frequency. However, such rigid rulers are in fact fluid in the TT. So there's a kind of a complicated sense of what is rigid, how am I defining my experiments. The experiments are usually not defined in the TT frame. They're more naturally defined in the so-called detector frame. This employs so-called Fermi normal coordinates. These are the natural coordinates of the experimenter marked by a rigid ruler, okay? So things that are very, very rigid remain rigid in this frame. As a result, effects are less subtle. They look like Newtonian effects at the level of a force or things like this that are perturbations away from flat space. And that's because this metric in the long wavelength or low frequency limit if you're arbitrarily close to your choice of origin compared to the wavelength of the gravitational wave, the corrections to the flat metric vanish. So this reduces the flat space when the wavelength of the gravitational wave is very long. And as a result, things are conceptually a lot more simple in this frame. Okay, so as a result, I'm going to be advocating for this frame. So let me show you how potentially a toy example, how things can go awry. Okay, so the toy example that I want to show from the point of view of thinking about how GR plays with electromagnetism is shown here. Imagine you have a gravitational wave. It's passing along the z direction where there's a magnetic field aligned along the z direction. Okay, so this is traveling longitudinally aligned with magnetic field. Now, as I told you before, this interaction between GR and electromagnetism will source some effective current, which will generate an oscillating electromagnetic field. And this oscillating electromagnetic field will drive a current on a conductor shown here in gold. Okay, that current is a covariant object. It's therefore approximately invariant in linear order. I can evaluate this current in any frame I like, and it should be the same. Now, just to define the problem a little bit, let me calculate the current driven on this conductor if I, let's say, nail this conductor to a wall by putting in a spring. Okay, so I'm just trying to define the problem as much as possible. But the right gauge invariant, right gauge invariant question to ask is, how large is this gauge invariant current that is induced on this conductor from going to here, from the gravitational wave interacting with the B field, generating an oscillating field that drives a current? Okay, any questions about that? Right. Okay. Yeah.
Do you have any, similar subtlety in the case of the, for instance, CMB, like in CMB case, I know that people usually define the gauge invariant quantity, right? So people also do the correlation, but in the case, people define a gauge invariant quantity, and
Right.
in principle, there is no detail about, when computing stuff, then people take gauge, specific gauges, but in principle, first we can define some, gauge invariant cosmological correlation and stuff from that, right?
Right.
So in this case, is it more complicated or?
It's analogous to that.
Okay.
But as you'll see, there is a preferred frame for the CMB.
Right.
And one easy thing is just to work in that frame and kind of forget about gauge invariance and just work in the frame of the observer, and then you never have to worry about it.
Mm-hmm.
But as you know, there are some well-known papers getting tripped up about gauge invariance actually quite recently, but if you have dark matter physics. So it's actually yeah. So, but it's sometimes right. It's sometimes tricky to work with gauge invariant objects, because then you're like, physically, what does this mean to me in my frame? But there are analogies. I guess I'll stop.
So you can sort of define some gauge invariant quantity, but in practice, it is better to just choose the frame.
Yeah, exactly. So to be careful, what I'm going to show you is this current is an order H covariant object, so it's gauge invariant and to linear order.
Mm-hmm.
So that's a gauge invariant object that I identify. And I'm going to show you, just to be careful, how you can do things in two different frames to get the same answer.
Okay.
But the simpler way that we then go forward with this is just to choose R frame.
Mm-hmm.
And not the TT frame is not R frame. And work in R frame and then not have to worry about something, which is kind of analogous to how I want to see if we have. Good question. Okay, so what does this look like in two different frames, the signal? Okay, so this is going to be kind of a funny way of defining the problem. Let me define the problem such that the B field is homogeneous and static in the TT frame. As an experimenter, you don't live in the TT frame, so you'd have to have some weird knowledge of the gravitational wave to do this, but we can define the problem. Okay. When you go through this, what you find is that the effective current vanishes if the gravitational wave is traveling along the direction of the magnetic field. So you'd be tempted to say there's no signal. There's no interaction, at least for this jump. Let's analyze the same problem in the proper detector frame. In the proper detector frame, you of course have to transform the gravitational wave from one frame to another. A B field that's static in one frame is not static and uniform in the other. You have to do these transformations. But more generally, for the reasons that this effective current vanished in the TT frame, it doesn't vanish in this frame. So you'd be tempted to say that there's actually an electromagnetic field induced on this side. So this is just a statement that the effective current is not a gauge invariant object. That's no problem, but mistakenly in the literature, this has been claimed that this gives rise to no signal. Let's see how the signal arises. So to see how the signal arises, we have to be a little bit more careful, a little bit more concrete. We're asking what is the current driven on this conductor that's attached to a spring. And let me define the spring to be stiff in the proper detector frame, R frame. Okay. Now, this effective current will source a signal field that drives current. I can calculate that. How does the signal arise in the TT frame? Well, a stiff current is actually a spring is actually a moving spring in the TT frame. So something that's stiff over here picks up an order h velocity, and something that has an order h velocity through a static B field gets a little Lorentz force on it, and that drives a current. So the signal kind of looks like it's coming from something else. It's coming from the motion of the spring. But when you calculate this current driven on the conductor here and the current driven on the conductor here, they're exactly the same. And it's no surprise. This is just, you've calculated the right gauge invariant object. Another way to say this, and probably the more natural way to frame this problem, is not where the B field is defined in TT frame static, but one where it's defined in R frame. So maybe an experimenter will turn on a big B field in R frame. What you find then is you get a current over here, just like you did before. You now have to transform everything to this. So the B field gets a little correction, the motion of the spring gets a little correction, and both of these things lead to the fact that the current driven on this conductor in both cases are precisely the same. It requires a little bit of 2 lines of algebra, but what you find is that the signal is exact. Okay, but like I was saying before, it's kind of confusing to work in this frame where everything in the experiment is defined in the detector. So the experiment itself, how electromagnetic modes look like, they're defined to look in a certain way in R frame. So just to be careful, it's typically much easier just to work in the proper detector frame and forget about all this stuff. Okay, then you kind of know that you're not making a mistake.
Right, so just to be clear, in the proper detector frame, the mass would not actually move. The signal you're looking for is a current.
Exactly. So the signal will arise from the gravitational wave interacting with the B field, generates a signal field, which then drives a current. And in the other case, so in this guy, so that's how it would work over here. In this case, there's no signal electromagnetic field generated from this interacting with this. It's just the fact that this guy's now moving. And there's a V cross B, a velocity cross B force or thing that will move charges. Or another way to say it is you would boost to the rest frame of this guy, and this B field gets a little electric field contribution when you boost to the rest frame of this guy, and he drives a current in the rest frame of the conductor. That's another way. But it's really just now the spring is moving. And it looks like they're coming from very different pieces. But this is why people kind of related, people thought gravitational wave would gauge artifacts for this, because this stuff is all very tricky.
Like the gravitational wave in the proper detector frame, the gravitational wave itself is not causing the spring to oscillate because it's transverse, like it's moving in the Z direction, but the metric is being perturbed in the X and Y direction.
Yeah, well, okay, so if the gravitational wave was absent, these frames would be identical. They only differ by order H corrections. So this is moving due to the gravitational wave. But it's because the frames are defined differently in the presence of the gravity. They differ by order H pieces, which would be 0. All these frames would be trivially both flat space if there was no gravity. So the gravitational wave is inducing the spring to move. In this frame, it's not, because the spring is arbitrarily stiff. But as soon as you know that a spring is not moving in one frame, I can tell you its coordinates in any other frame that I find just by transforming those coordinates in the appropriate manner. But that coordinate transformation is defined by the gravitational wave, which is non-trivial. So it's not, but here it's not like you don't think of this moving because you wouldn't think of this moving because it's like a tidal force of the spring, where that's how you usually think of stuff moving in our frame, because the gravitational wave acts like a tidal force. It looks like a Newtonian tidal force or something. Here it's a little bit more subtle, but it is moving because of the gravitational wave.
Okay. Okay. This is just not moving because it's arbitrarily stiff.
Yeah, exactly. Right. So like the displacement of this is, let's say the gravitational wave is at a hertz, and you make the first acoustic the first vibration of the spring at a megahertz, like that, the speed of sound of the things. I think it's still do that. So you just make the speed of sound of this material very high, and you decouple the perturbation of the spring will be decoupled in the limit of the gravitational wave frequency is much lower than the resonant frequency of the spring. That's how you make it stick in practice. Great. So, any other questions before I move on? Okay. So, with that understanding, we can actually now think about how these give rise to signals in real experiments. So, I'm going to be talking about how this can give rise to signals in so-called axion dark matter experiments. These are experiments where you have a hollow cylindrical resonant cavity. You apply a static magnetic field to that system, and you look, in the case of axion, looking at axions exciting the cavity if they're on resonance. And you'll see there's an analogous effect for a gravitational wave exciting the cavity on resonance. So just said again, you apply a static B field, either a gravitational wave or axion dark matter comes through, oscillating at frequency omega. And in both cases, you can phrase things in terms of an effective current that will generate a signal field. The axion one is defined in terms of the axion field and the axion coupling. I'm not going to talk about axion physics at all, but I'm borrowing the nomenclature, so that's why I'm doing this. But if you wanted to get a quick estimate for how sensitive these experiments are, the first step you would do is to ignore all the differences between gravitational waves and axions. You ignore the fact that one's tensorial, one's scalar. You ignore the fact that they might have different spatial or temporal profiles. You just equate these currents. Okay. What you would find is if you take the sensitivity of something like ADMX, one of the leading axion experiments, and you just translate that into the effective strain, it's just this coupling times axion field. It's roughly 10 minus 22. Okay. So that's a minuscule strain, but it would only be sensitive to gravitational waves at very, very high frequencies, like gigahertz, which is where these resonant cavities operate. And as you'll see, I'm going to take you through a more detailed estimate. This turns out to be right up to order one numbers. It doesn't tell you anything about angular sensitivity, gravitational waves, things like that. But this is roughly the right dimensional estimate. Okay. So one small complication that arises, and this is one reason that people usually do not employ the proper detector for doing calculations, is that in any textbook that you open, or 99% of papers, if you look up the form of the metric in the proper detector frame, the one I'm advocating for, it's usually only quoted the leading order in some Taylor series of the gravitational wave times some distance from the center of mass of your system. Okay, and then maybe there's some famous papers that go to the first two terms and some other famous papers that go to the first three terms. But we're interested in where these cavities are resonant, which only happens when the wavelength of the gravitational wave is comparable to roughly the radius of the cavity. So we can't use these Taylor expansions. We have to use the result in this case. And what we found, which surprisingly just does not exist and predominantly in the GR literature, it might exist in some small fraction of papers that I've not come across, is the form of the proper detector frame where you include the full set of terms. Okay, so what we found is you could do this Taylor series and you can sum them all up for a single Fourier mode, which as far as I know is not really entered in any of the text. But this is the form of the metric in the proper detector frame. The stuff in black is the usual textbook stuff. I don't have an equation here just to show you there are equations. I don't expect you to absorb what per se. But the things in black are just the standard textbook results. The things in red are the generalized corrections that we found. And these corrections reduce to 1 when the frequency goes to 0. So they just reduce it to the standard answer. But now you can calculate the metric for any frequency gravitational wave exactly, at least for a single Fourier mode. Okay. So this allows us to work in this limit where the frequency of the gravitational wave is comparable to the size of the apparatus, and we don't have to Taylor expand these things. So you can use that machinery, and here's a cross section of the cavity. Okay, let's say here's a cross section of the cylindrical cavity. I'm going to apply a B field going into the screen, and just to preserve symmetry, let me imagine there's a gravitational wave coming into the screen as well. What does this look like in terms of how it couples? Now you can calculate the effective current exactly. What you find, not surprisingly, is that the effective current has this kind of quadrupolar spin-2 nature. Okay, so you can actually understand this thing quite well, and you can answer what is the optimal mode, resonant mode, that this current will couple to. For this current to couple to the cavity, it had to have a large overlap with the electric field of the mode integrated over the volume. So you want J, the current, dot E, the electric field of the cavity, integrated over the volume to be substantial. And there are modes that look roughly like this, not exactly like this. But for instance, a transverse electric mode that is spin-2 in some way looks very analogous. By eye, you can tell this thing should have a large spatial overlap when you dock them into each other and integrate. And you can do it in its order of one at the level of 0.1 spatial overlap. So what this means is that for a gravitational wave coming into the symmetry axis of the cavity, the optimal mode is something like a transverse electric. This guy, where the electric fields are in the transverse direction and have spin tube structure. But this is not the mode that axion experiments use. They use so-called transverse magnetic modes, where the electric field is along the longitudinal direction, not along the angular direction. This means that generally the most optimal mode for gravitational waves coupled to these systems is not the most optimal mode for axions, especially when you have the cylindrical symmetry. The gravitational wave is coming in along the symmetry axis itself. However, what you find is that if the gravitational wave is coming off axis, more or less any mode will couple. This is showing you some geometric coupling as a function of angle of approach of the gravitational wave, the same here. The left is showing you the coupling, this geometric coupling, which ideally should be order 1 for transverse electric modes. The other one is transverse magnetic modes, the modes employed by axion experiments. And what we find is that for a gravitational wave coming in off axis and coming in from the side here of this cavity, the coupling can be at the order of 0.1. So it's not perfect, but it's good because this means only a reanalysis of existing data in principle is needed to place a bound on exotic sources of very high frequency gravitational waves, narrowly centered around here. So when you do a full calculation, this is what you find. This is roughly the strain and sensitivity to very coherent gravitational waves at a gigahertz of different experiments. And what you find is that they kind of line up with the tilde estimate, at least for ADMX, at the level of 10⁻22 or so. And this hash thing is maybe a future version of such an experiment where things can be scaled up. Maybe you can get another order of magnitude in strain. But you can see at the end of the day, our tilde estimate was basically right. And we can understand the directional sensitivity, the polarization sensitivity exactly.
So the signal is proportional to h squared or
the signal power. Yeah. Yeah, that's right. But the effective strain that they're already programmed is 10⁻22 or so.
Gaining 1 order of magnitude and h being like 100 times.
Yeah, exactly. So this was what's the big gain here? The big gain was a bigger quality factor, comparable magnetic field, a bigger volume. So yeah, a slightly smaller temperature or comparable temperature. So here the big gain was a higher quality factor and a bigger volume. Okay, this is interesting, but you know, there are not a ton of well-known gravitational wave sources at gigahertz aside from some very developed, maybe like alien civilization trying to communicate with us at a gigahertz. But so to me, this is interesting. You just have to reanalyze data, but it's maybe not the most interesting frequency spectrum to look at for gravity. So the question is, how do we extend this frequency band? Okay, are there similar games we can play? Not look all the way up at a gigahertz. Usually, the lower frequency range you go within this high frequency band, the more interesting it is. Okay, and this is because there are sources of BSM physics that might give rise to such sources, not at a gigahertz per se. They might be detectable more at a megahertz. So that's what I'm going to tell you about in the last 20 or 25 minutes. This is based on work that's hopefully going to come up very, very soon. We're delayed because we're confused about a factor of 2. Hopefully this will be resolved soon. Okay, I'm going to basically the idea is to take an experiment that was actually built around 20 years ago. I'm going to rebrand it by calling it a Weber cavity because it operates analogously to a Weber bar. And we'll actually show that it was actually, even though it was kind of killed, the effort was killed around 20 years ago, we think it's actually much more powerful than it was originally thought to be to look for high frequency gravitational waves. Okay, so here's the picture of the experiment. It's called Mago, the microwave apparatus for gravitational wave observation. This is a collaborative effort in Europe between INFN and CERN. What it is this funny looking superconducting cavity consisting of 2 superconducting spherical cells joined by a thin aperture. This little ring here, so you can squeeze the aperture. I'll explain why that is optimal. It's made out of superconducting material because these so-called SRF or superconducting radio frequency cavities have very low loss very high Q. So in the language of a damped harmonic oscillator, they have a very high quality factor. I'll explain what that means. But their coherence time, even though they're oscillating every nanosecond, their coherence time is on the scale of seconds. So they're extremely coherent under damped objects, meaning that you can amplify a signal. So this was built, had fantastic, it operated great. They didn't do a search or anything, but they were testing it. It was eventually, I should say, also it originally dates back to some theory work of some Italian physicists going back into the 70s. So theoretically, it's actually roughly 50 years old, but this is roughly 20 years old, this thing. It was pulled because eventually became apparent that these people should join Virgo. The funding was pulled, the personnel was pulled, and they moved over to Virgo. But today, here's a recent picture, actually from somebody we know. We took a picture of this thing. It's currently like a museum piece. It's sitting behind glass at the University of Genoa. Okay, but the hope is we're actually going to take this thing, dust it off, and it will probably live at some linear combination of 35 and actually use it. Let me describe why this thing has a. Well, I'll get to why this thing has a funny shape. But let me describe what the signal is. The basic idea is you drive a large amount of power, electromagnetic power, in one of the resonant modes of the cavity, mode 0. Okay, where this is some resonant mode, electromagnetic fields oscillating at omega 0 around gigahertz. Now, a gravitational wave, let's say at a megahertz, much lower frequency, will couple to the system in various ways. There are various kinds of signals that can. One is the same kind of direct photon coupling, where the graviton comes in, interacts with these photons that are living there and excites it to a higher energy photon. The other signal, which turns out to be more powerful, is that the gravity wave just shakes the walls of the cavity, analogous to a Weber bar. It shakes the system. And this will excite the photons from mode 0 to mode 1. So the gravitational wave interaction with mode 0 will excite mode 1 if the frequency difference between mode 1 and mode 0 is comparable to the gravitational wave. So ideally, you'd like this to be a resonantly enhanced process. You would tune this thing such that, let's say, mode 0 is at a gigahertz, mode 1 is at a gigahertz plus a megahertz, and therefore a gravitational wave at a megahertz would excite the signal mode that you then read out and infer this kind of thing. Let me take you through that again, just so we're on the same page. This is showing you the differential power per unit frequency. So once again, drive a pump mode at a gigahertz, a large amount of electromagnetic power oscillating at a radio frequency. Gravitational wave at a much lower frequency couples to this pump mode and acts like a source term. I'll explain how that's the case. It acts like an electromagnetic source at a linear combination of those two things. This means, generically, let's say you weren't going to tune the cavity. Generically, this source would be out of resonance with the signal mode, which is also near a gigahertz, but slightly excited. Generically, this would excite the signal mode off resonance. I'm going to be calling that a non-scanning or a broadband search. And even then, it's actually quite powerful. I'll explain how so. But even if the signal is off resonance, it's quite powerful. But the more powerful treatment is if the gravitational wave is very close to the frequency splitting between mode 1 and mode 0, then it will resonantly grow the field to be a much bigger field. And generally, you can tune the splitting between mode 0 over here and mode 1 over here by squeezing that funny little aperture connecting two halves of the cavity. Okay, so I mentioned before that the quality factor of the system is important. This is so-called Q factor is just roughly inversely related to the friction or the loss or the damping of the system. And what this means is that if you have some driving term of a harmonic oscillator on resonance, for instance, the electromagnetic field amplitude will grow linearly in time until it saturates after Q oscillations. This means ideally you want something with the largest possible amount of Q, because this means you have the longest amount of time to resonantly drive power into the system, thus amplifying any initially small state. Okay, and the great thing about SRF cavities is you don't know, out of all macroscopic oscillators that humans have ever made, they're the most efficient. So they have the highest quality factors. They oscillate 10 to the 10, 10 to the 11 times before there's damping happens. So you get a lot of growth in the signal if the signal's on resonance. Okay, so as I mentioned before, the signal can arise in two different ways. The so-called direct coupling between gravitons and photons, or the indirect coupling where the gravitational wave just shakes the walls. Both of these things can lead to a signal. The first one is the so-called inverse Gertzenstein effect that I described before. The other one turns out to be more powerful, and it's operating like a Weber bar. There are these big bars that you look for the shaking of to look for gravitational waves. In fact, the first gravitational wave detectors, or trying to be the first gravitational wave detectors. So I'm going to call this a Weber cavity. It's essentially a hollow version of a Weber. As you'll see, this mechanical signal where the walls are shaking as induced by the gravitational wave will be the dominant signal because acoustic vibrations are much less stiff than electromagnetic vibrations. And this is coming from the fact that the speed of sound is much smaller than the speed of light. Mainly, if I have a gravitational wave shaking the walls, if it's shaking the walls fast enough, you don't really care about the intermolecular response of the system. Okay, the acoustic resonance of this thing, the lowest one is at the level of a kilohertz or 10 kilohertz or so. So a gravitational wave oscillating at megahertz doesn't care about the intermolecular responses, but it does care about the frequency of the electromagnetic modes, which are much more stiff. So we'll see how that plays out. But this is the better signal. Okay, so let's see how the signal works. I'm going to be writing everything in terms of the strain, in the proper detector frame. Just don't be confused. People almost always mean the strain in the TT frame. This is related by a factor of frequency and a length scale. But I'm going to be comparing these two things to each other. It's simpler if I just write things in the proper detector. So the proper detector frame, this direct photon interaction sources a current, like we talked about before. On resonance, that current just excites. The current is proportional to the driven field, we're calling E0, and it excites a signal field that looks like is of the same strength as E0, but suppressed by the tiny strain and enhanced by the large Q, the quality factor of the system. Okay, now that's kind of quick. The mechanical signal is a little bit more complicated, so I'll take you through that. In the proper detector frame, the way that this arises is that a gravitational wave looks like a tidal force oscillating the walls of the cavity, just shaking the cavity. Okay, that's proportional to the mass of the cavity and the strain as well. That displaces the cavity walls by some small amount, some small distance, delta x, which looks like this acceleration times some time scale squared. Okay, that time scale is the shortest one of either a gravitational wave oscillation or an acoustic resonance time scale, where the acoustic resonance is roughly the speed of sound over the size of the cavity, the time it takes for speed of sound to propagate, okay, across the cavity. Now, the great thing about this system is that the speed of sound is very, very small. So this enhances this overall quantity. So this little perturbation in the wall, as it shakes, mixes the two modes. Okay, you can think about it like a perturbation to the Hamiltonian. It will mix mode 0 and mode 1 and cause some form of Rabi-Flop between these two modes. You want to call it mechanical analog with that. But it will excite the signal field proportional to that little distance, delta x. And when you go through it, the signal field looks just like we had over here. Okay, except I have this additional piece. And because the speed of sound is extremely small, typically, level of 10 to minus 6 in this material, this means this factor, this 1 over this factor is extremely small. If the speed of sound was 1, looking for gravitational waves below a gigahertz, these two quantities would be precisely the same. But because the speed of sound is 10 to minus 6, at very, very low frequencies, this is a 12 order of magnitude gain in the signal. At intermediate frequencies, where omega g times some length scale is actually the bigger quantity, then it's less of a gain, but still quite a substantial gain. But as soon as you drop below a gigahertz in frequency, which is roughly 1 over the length of this cavity, you start parametrically gaining signal power, So for the rest of this, I'm predominantly just going to be focusing on this signal, which once again is coming from the gravitational wave, shaking it, mixing the modes, and causing power transfer between one mode and another.
Does this indirect signal also exist for like the axion experiments you were talking about before? Like, can it like drive certain modes?
So it can be a noise source. Well, okay. Well, so for the axion doesn't induce a mechanical force on things, but if it was like a dilaton coupling.
Oh no. I mean just like in like ADMX, but still looking at gravitational waves. Like why do you always talk about the direct?
The answer is no. I can. So okay, so it turns out the answer is no because the signal or the pump mode, what you're pumping in ADMX is a static B field, and that's a very important difference. Whereas here, what you're pumping are oscillating E and B fields, the full electromagnetic mode of the system. Whereas what you're applying to ADMX is just a static B field, so it's not a mode. So that's the important difference. And when you go through it, it turns out shaking the walls can't be a signal for ADMX. Another way to see it, this is a more intuitive way to see it, is that let's say you take let's approximate ADMX is just a sheet of metal in a magnetic field, and you're asking if I shake the sheet of metal, will that excite a resonant mode of whatever open cavity system I'm describing? If you shake that conducting sheet in a magnetic field, it will drive currents in the sheet for sure. There will be currents, but the resonant modes of a cavity are defined such that J dot E, are defined such that the electric field at the surface of the conductor has no tangential component.
Okay.
So J dot E, J the tangential currents in the wall, and the normal mode have zero overlap. So that's kind of another way to say that if you take ADMX and just shake it, it won't excite a resonant mode. It will emit radiation. I mean, you'll have a current in the walls, but it won't be a resonant mode. Or maybe it's some like, you won't resonantly grow. It will be some small electromagnetic field, but the signal's very good. Okay, that's a good question. We thought about that a little bit. Okay, so I'm going to tell you a little bit more about why this geometry is so funny. Kind of looks like a melted dumbbell. We actually drew it this way because it makes explaining the geometry a little easier. The real one doesn't look melted. It looks a little bit more solid reality. So the idea once again is to drive a signal mode, the mode 0, and look for power jumping in the mode 1. It turns out that these modes, there can be two modes in this coupled system that are very close to each other in frequency. That just differ in how the linear combinations between the two halves. So the lower frequency one will look like a symmetric linear combination between the left and right of some single cell mode. I take a single cell mode, I just copy it and make it symmetric. The slightly excited one, the signal mode, will be an anti-symmetric one because it has some gradient energy associated to it. And the reason for this is actually one, it's easy to get small frequency splittings between two systems like this. Two, you can actually use smart readout. So the Mago people back in the day had a smart readout system where they either took a sum of the mode profiles or the difference of the mode profiles. Because one is symmetric and one is anti-symmetric, you can distinguish these two things very, very well. And remember, you're driving a large amount of field in mode 0. You want to read out in the same cavity mode 1, which is extremely small. So geometric discrimination is extremely powerful. And what they were able to do around 20 years ago is get 14 orders of magnitude in power rejection in these two modes. So this means that any kind of noise creeping in from the fact that I'm trying to read out mode 1, but I'm accidentally reading out mode 0 when I'm driving is extremely suppressed because I can geometrically discriminate these two things. Now, furthermore, as I was saying, you can tune the splitting between these two things very well. This actually dates back to a famous paper by Hans Bethe when he got interested in cavities for some reason. But you can show that this frequency splitting between the anti-symmetric one in blue and the symmetric one in red goes like the small radius of this little aperture here over the big radius of a sphere cubed times the overall frequency of the system, which is gigahertz. So you can get very small frequency splittings between these two things just by squeezing the radius of this aperture connecting the two halves. Okay. Now, we go through this. The final technical thing I just want to say is you can actually calculate the overall coupling of the mechanical vibrations to the electromagnetic system. So how well does a vibration excite jumps in power from one electromagnetic mode to another electromagnetic? It turns out to be roughly just controlled by these modes dotted into each other, and then weighted by the normal component of the displacement of the wall integrated over the surface of the cavity. What you find is that for most directions of a gravitational wave coming in, this thing has non-zero overlap. There's really no symmetry to prevent it. But generally, this perturbation is like a quadrupole, the kind of a mechanical deformation that is induced by the gravitational wave is a quadrupole. You get stretching in one direction and shrinking in the other direction. So this is a quadrupole, and these quantities dotted into each other can easily be a quadrupole. So when integrated over the surface, this thing is non-zero. So it turns out we can actually do the stuff semi-analytically. So this is that coupling. So this coupling the geometric coupling. So how good of a mechanical to electromagnetic converter is this thing for gravitational waves. This is what the coupling looks like, essentially a sky map and equatorial coordinates. The bright spots are good coupling, dark spots are bad coupling. You kind of have to be pretty tuned to have zero coupling. But for most regions of the sky, you have some kind of coupling in regions where the coupling is large. Okay. Now, I'm going to say a few words about noise. This is most of the work over the past few years in understanding these kind of big experiments that we've done. This could be a talk in its own right, but I'm just going to take you quickly through a discussion of what are the dominant noise sources. There's many things that can occur. Now, in a scanning setup, let's say where you take this frequency splitting and try to match it to the gravitational wave. Okay. So essentially, I'm assuming that the experiment is scanning for every frequency of gravitational wave here. Here I'm showing you the power spectrum, or the power per unit frequency in either the signal in blue, which is some arbitrarily chosen signal, or noise. Okay. What we find is that for low gravitational wave frequencies, the dominant noise is shown here in green, which are just noisy vibrations of the cavity. Okay, the gravitational wave trying to vibrate the cavity, but so is the world. And that constitutes some noise. Near these little spikes are mechanical resonances of the system. So if you were to look for a gravitational wave, happen to be very degenerate with a mechanical resonance of your cavity, you'd have some large contribution from a mechanical resonance being excited by some noise source mimicking your signal. At high frequencies, what we find instead is this pink curve. The electromagnetic noise is the dominant noise source. This is essentially just thermal occupation of the electromagnetic noise. So cavities have resistance just due to and they have a temperature. So because they have a temperature, they emit radio waves, and those occupy the modes you're trying to do research in. That's suppressed by the small temperature of the cavity, but really importantly, it's suppressed by the large quality factor of the cavity. And this is because the quality factor that I described as ringing up the signal is just inversely related to the resistance. Okay, so if you have a larger Q system or a less noisy resistor, that contributes less noise. Okay. So this is often called Johnson-Nyquist noise, but it's suppressed by the high Q. And this is a really important point. As you'll see, Weber bars also have electromagnetic readout, and their Q is many orders of magnitude lower. So this pink curve for Weber bars orders of magnitude higher. And so it's really this thing is the main differentiating feature compared to a Weber bar, other than the fact that a Weber bar is typically a big ton scale experimental distance. It's the Q that really suppresses the noise. You can also ask, what happens if I hold the frequency splitting fixed and look at noise contributions? What you find once again is at low frequencies, mechanical noise. At high frequencies, it turns out to be noise just from the read amplifier. These are kind of technical details about noise that I can talk to you about, but the main important thing is that thermal noise is suppressed by Q. Okay, so high Q suppresses electromagnetic noise, and this means when you're looking at a gravitational wave away from a mechanical resonance, so away from these little peaks, you're often limited by this pink electromagnetic noise, and that's suppressed by this high Q. So the comparison that I want to make is to a Weber bar. A Weber bar is more or less just this. It is also a mechanical to electromagnetic converter, because a Weber bar is a big ton scale thing, a lot of mass because of gravity. It shakes, and its shaking displaces, the way they read it out is the shaking displaces one plate of a capacitor that's sitting in some bias E field. So you apply an E field to the capacitor shakes, that drives a voltage in the circuit. And that shaking is at the frequency of the gravitational wave and resonantly rings up the voltage or the current in the circuit. So that's how Weber bars are actually read out. But the problem is that Weber bars, LC circuits are typically much higher resistance systems than a hollow superconducting cavity. So their electromagnetic quality factor, as opposed to 10 to the 10, are more like 10 to the 6. So this means that if you're away from a mechanical resonance, the dominant noise source, the electromagnetic noise, is actually extremely limiting for modern day Weber bar experiments. And it's the main differentiator between what I'm talking to you about now and how Weber bars operate. So on top of a mechanical resonance, these things will of course be better. But away from a mechanical resonance at higher frequencies, they are very limited by LC circuit noise, and it's much larger than the electromagnetic noise of a superconducting cavity. So, okay, So now, let me show you what the reach looks like. So this is the sensitivity to coherent gravitational waves. So some coherent strain H as a function of the frequency of the coherent source. This, ignore the blue, this is the electromagnetic signal that I said is very subdominant. The purple curves are the mechanical signal from shaking the walls. This purple curve is what we think you could do if you built an experiment like Mago that could scan across this whole frequency range. Mago was not scanned to scan across this entire frequency range. They were kind of limited to live around here. And putting in our best noise estimates for what noisy vibrations look like. These non-shaded purple regions, for instance, this one shows you the reach of a similar scanning experiment, where instead the vibrations have been attenuated down to their irreducible thermal bound. It's just because if something has a temperature, it's shaking around just because it has a temperature. Whereas this curve is saying, actually, there's a lot of reducible vibrations that we can measure and put into our estimates. This one is the irreducible. This dotted line is assuming, let's say you're being lazy and you don't want to do a scanning experiment. You just take the Mago instrument as is, you fix, let's say you don't want to scan over a big frequency range, you keep it fixed at a certain frequency, and you just try to read out all frequencies and do a non-scanning or broadband search. That would be the reach here. And in principle, it's not as good as a scanning experiment, but much easier to do in principle, and might be smarter to do if you think there might be transient sources of gravitational waves that might be on at one point and then off at another point. Scanning experiment might miss it as you step through the full possibilities of frequencies. These gray regions are current exclusions. Origa is a Weber bar. This is a pulsar search by LIGO and Virgo, which is not exactly apples to apples, but roughly appropriate. This green region is where we think some new physics signal might live. I won't go into this in detail, but this is a class of signals called superradiance, where, let's say, a nearby spinning black hole generates a cloud of bosons, new beyond the standard model bosons. Those bosons then annihilate the gravitons and generate gravitational waves. So here, the frequency of the gravitational wave is fixed by the mass of the boson generated around these spinning black holes. And as a result, you can, we're essentially dialing the mass of the black hole frequency. Above 100 kilohertz, this not just requires new bosons in nature, but also requires primordial black holes. These black holes would have to be self-solar mass. This way, 100 kilohertz down, you just require a nearby solar mass or heavier black hole generating these classes of signals. Yeah. You could also ask, what is?
Sorry.
Oh yeah.
Got a couple of questions. So you're talking about subsolar mass black holes.
Yeah.
What mass? How does it scale?
It's right here. So at 10 to the 5, it's roughly a solar mass, and for every decade you take, you dial down a decade in mass. So this would be 10th of a solar mass, 100th of a solar mass.
Okay, so they're not real small.
What?
They're not real small. They're just
That's right.
Big planets.
Yeah, that's right. That's right. Not bigger than an asteroid for sure. From the point of view of astrophysics.
Right. I'm sorry. What is BAW?
Oh, sorry, I didn't tell you about these. BAW is bulk acoustic wave resonator. These are small piezoelectric resonators that have very high acoustic modes and very high mechanical quality factors. They were built by Michael Tovar and others to look for gravitational waves around megahertz. But it's a small mechanical and resonant antenna.
Okay, and that vertical band there, that's Fermilab.
Yeah, this is right. Sorry, I should have told you that. This is the holometer, the small interferometer at Fermilab.
So the advantage with your proposal is that you can cover much broader
That's right.
spectrum.
That's right.
If you wanted to do this scanning approach, how long would it actually take you to scan this entire?
Good question. 15 years. we fixed the E full time to be about a year.
Okay.
So around the decade.
And like for these super radiance signals you're looking for, the super radiant clouds, would be longer lived than.
Oh, yeah, they're
15
highly,
years, right?
yeah, they
So-
drift because there's a small drift to the signal because as the bosons are annihilating away in the gravitational waves, they're going from a more tightly bound gravitational system. It's reducing the mass, so it's less gravitationally bound. So the frequency is very slowly creeping up as these things become less bound, so the mass is decreasing. But the drift scale, it's a function of frequency. I forget exactly, but it's typically on the order of hundreds to hundreds of thousands of years to drift across like a significant portion. Yeah, so typically very, very.
Okay.
And so these are highly coherent signals. I'll just finish by showing you. Sorry, I'm going over this is the very end. By showing you the reach to stochastic sources. So essentially, this is just a noise plot. It's a strain equivalent noise of the system, which would approximately be the reach to a stochastic source. Because some stochastic gravitational background would be indistinguishable from some new noise contribution that you don't understand. This is where we actually compare ourselves to other projections, because now you don't have to assume when people make projections, they assume something about the high frequency source, they assume something about scanning strategy, and it's always different. But if you make a curve like this, it's more apples to apples. This is people have talked about building big LC resonators with gravitational waves. That's this. People have talked about levitating very big dielectric stacks at the level of cubic meters. So this is all pretty futuristic. And what you can see is if we can just take the Mago cavity and or something like it, and just reduce the vibrations compared to just typical vibrations if you would just put it in a lab. So you'd have some kind of vibrational isolation. You could do a reach that's actually quite impressive. Oh, this is where primordial signals lie, to not overclose the universe. So this, you know, if you have a way to go from here to here, then it's interesting. But this is kind of why I have columns when people talk about looking for high frequency gravitational waves to look for the early universe, because it is many orders away. So we're not looking for such sources, but lower frequency instruments could very well be.
Sorry, that was not ineffective, right? That was
No, this is way worse than
Okay, okay.
way more conservative. This is just saying I don't want to have more energy density than the critical. Yeah, ineffective would be pushing it down.
So it's looking for more recent history,
I mean, one way to say that.
something more local,
One way
right,
to-
rather than filling the
Yeah.
whole space.
And you could of course have a stochastic like nearby source. that's not
Yeah, that's
going-
right. That's
in which case you could interpret this. This is just this would be to me the most interesting thing, but is not within the realm for anything that anyone's thought of, at least at high frequencies. Okay, so let me just conclude. Sorry for going a little bit over. The frame dependence of electromagnetic signals for GR are subtle. Hopefully I convinced you that it's always, if you want to do a calculation, the safe way to do it is to work in the proper detector. Math is a little bit harder, but conceptually, things are always much easier. As a result of that, we were able to make the statement that axion experiments only need to reanalyze data. In fact, we've been talking to ADMX and Haystack, and they're both interested in this. And in fact, they've emailed us when they've seen unexpected signals and asking, could it be a gravitational wave? Answer's probably no, but it seems like they're interested. And this other experiment, Mago, this weird double cell cavity that I was talking about, is more powerful than previously appreciated by a lot. So as a result, we're trying to get this out of the glass, and it seems like it'll probably live at some linear combination of Fermilab and Lindsay for processing and treatment and getting it back up. Apparently, you can't just take a cavity that's been sitting around for 20 years and run it and expect it to be fully operational and treatment. Opportunities theoretical. The biggest one in this community, I think, are there other high frequency targets that we're missing? More or less the only ones are the mergers of really light primordial black holes, which I didn't even show because those targets are actually much lower than what I was showing before, or super radiance. Are there other things that people haven't yet thought of? I think there's a lot of effort worth thinking in that direction. I think this story about axion-like signals or axion-like experiments also being sensitive in principle to gravitational waves is probably much more general. So for instance, people have thought about axions coupling with spin. Gravitational waves also couple the spin. So it's probably the case that there are other things to think about on how to hijack axion-like ideas and turn them into exotic gravitational wave detection ideas. This isn't the end of the story. I can talk more about that. Thanks.
So do we have any questions for Asher?
Does that mean you will have some annual or daily modulation for the signal for gravitational wave if you have the direction sensitivity of where it comes
Yeah.
from in terms of the cavity direction?
Yeah. So you would definitely would as the Earth rotates. So, in fact, because it is so directional for these cavities, with a couple of them, you could probably pick out the location and polarization quite easily. Although we haven't done that analysis, so I'm not sure exactly how true that is, but it is extremely directional. So maybe just having a couple of them. One, you'd see a signal modulation. But that typically doesn't help you in terms of discovery potential a ton. But it would help you in terms of confirmation.
I see.
But it's also helpful for trying to characterize a gravitational wave signal if you really see it. But yeah, there's definitely a big daily modulation for most sources that are localized.
Can it be used as a way to suppress the background? Because
I mean, so you can do some like optimized like template analysis.
Yeah.
It typically doesn't help you a ton. That typically doesn't help you a ton because one way to think about it is let's say you're looking for a coherent signal. When making those reach curves, you're basically assuming you're doing like some optimized waveform analysis by taking whatever you're reading out and convoluting it with a sinusoid to try to read out the sinusoid signal.
Yeah.
If it's an oscillating signal and there's a daily modulation, that's just going to take the signal and put it at beats. Like let's say the signal was at a megahertz. It's going to put it at a beats at a megahertz plus or minus 1 over a sidereal day. So it's just going to modulate where the frequency lives in frequency space. So you would do a very similar analysis. I mean, but you can also play games like building up more detectors. If you had 2 or 3 detectors, but that typically only helps you by a factor of square root of 2 or square root of 3. So nothing, as far as I'm aware, can buy you a huge parametric gain, but it could buy you maybe order 1 gains. But it would definitely be important if you see something, and then you want to confirm that it's like outside of our planet. Then it would be something.
I also want to ask, directional information for it. So ADMX case, I understand that, it depends on the direction of what kind of model you decide. So from that, you can get information about the direction. So how about Mago case? Like, how you can be sensitive to the.
Well, so I think I had.
Okay, this one.
This one. Yeah, so this is the coupling as a function of position on the sky. This is, I forget exactly what polarization we picked. This was for a fixed polarization, obviously. So if you change the polarization, the spots would move around, but we'd have roughly the same pattern. So if you built it's kind of a dual spherical system, so it has good coverage across all the sky, and it's polarizing the electromagnetic modes. Because the modes living in the cavity are polarized, by the fact that you have to stick an antenna and that breaks the symmetry of everything. Now they're sensitive to a particular direction.
Was there something that the previous Mago people missed, or like why did people underestimate the sensitivity of Mago? Or did they just give up?
They never actually, as far as I'm aware, like fully went through a full analysis. They said this is what the noise levels could be. They didn't consider the possibility of looking for signals outside of the resonance, which is what we did. So even if you don't tune it, you can actually you do a broadband search where it's off resonance. And the reason that works is because the signal gets parametrically suppressed because you're away from the resonance, but so does the noise, most noise sources, not all. But as a result, you can actually have great sensitivity outside of the resonance. That's one thing they missed. Also, in doing this kind of work in the past few years, we've kind of gotten a better understanding of how to build in noise estimates. So what they were doing was kind of quick and dirty. and for the signal too. So there's some differences in noise estimates, there's some differences in the signal analysis. But yeah, I mean, the technology was already there, and it looked like it was good to go, but then everything was kind of cold. When they were told to join Virgo. So maybe they would have appreciated it, given a little bit of action power.
So on the topic of like other sources, there was this paper we talked about in Journal Club at some point about like, I think, like phase transitions in neutron stars.
Oh, I know that paper.
Yeah.
Yeah. That, how was it like a megahertz or something? Or-
Yeah, I think it was like megahertz.
Yeah, I haven't completely outside of my expertise, but we did one person in our big theory collaboration pointed out that paper, and it's cited in the paper that we're going to put out.
Okay.
Yeah, but we didn't put a target for it. Maybe we should. It was way beyond what I'm familiar with to say, to be like a judge on this and be like, is this realistic? Is it? Yeah, but yeah, that's a good point. That is potentially another aspect of this.
Yeah, okay. I think we were in a similar boat. We don't-
Yeah.
Yeah, I was a similar question, but somehow sort of turned around.
Uh-huh.
I mean, how much energy would a source need at a reasonable distance, say within the galaxy, in order to be detected?
Good. Okay, so I don't have the answer in terms of energy off the top of my head, but I can give you an example which might help quantify it to some degree.
Or normalize it.
Yeah, so we did an estimate for the merger of light primordial black holes that might be nearby. Because if they're very light, they can spin a very high frequency and maybe get a signal. The estimate that we found is that they had to be within a distance of very sub-parsec to be detectable. And part of that might have been actually too much of a penalty because we were requiring that that the frequency emitted by the binary was not sweeping over a frequency range too quickly, because this is a very narrow resonant experiment, and we wanted the signal to fully ring up the resonance. So typically what that means is you want something to fully ring up your resonator for a long time. You want the drift in the frequency to be small, or the omega dot to be small, and that means you want the masses to be small. But making the masses small, of course, makes the strain small as well. And I think for that estimate, it had to be like within an AU. So completely crazy. If you relax the requirement that it fully rings up your resonator, I forget. I think it was on the order of a parsec. Or high frequency, like a megahertz or something, where I forget exactly what mass that was at. I guess like a hundredth of a solar mass or something. I think we found that it had to be on the order of a parsec away to be detectable. But I'd have to look back at our estimates. This is just kind of drawn from some old memory. I mean, another way you can see it too is that the cosmological energy density would have to be very, very high for these things to be detected as well. Many orders of magnitude of critical. So maybe that's the better answer to the question.
Well, I guess, of course, that's a problem, because if there's one within the parsec of us, then there's probably a whole bunch more within the parsec of spheres, all throughout the universe.
Right.
Well, or just the rate is very slow. It's very low.
Yeah.
Or the rate is very low.
Right.
Right, because
Yeah, but they want to see one, right?
but you can estimate if you're assuming they're the dark matter or whatever. If you assume a number density of these things throughout the galaxy,
You can
estimate how many are going to be within one parsec.
Yeah, we did that, and it was not interesting enough to put a target in there.
You need some dark sector transition nearby.
Late.
Yeah, you accumulate stuff in the center of the sun. It sort of sits under its own pressure, but sometimes there is some, like similar to core collapse supernova, right? There is a transition in the center. I mean, I'm trying to reach out to the maximum signal that I can think of.
Go for it.
Yeah.
Don't stop there, keep going.
And then you have periodic kind of jolts, right? You don't have any good model for that.
Yeah, unfortunately, there's not a lot of good ones. But, and the nice thing is, it's so easy.
That will be 1 AU away.
There you go. But unfortunately, like it's so much easier to do these high frequency searches that the lack of targets to me is not a huge dissuader from actually doing these things because it's they seem pretty simple. If this was building some big, large scale effort to look for something and you don't have any targets.
Is there any sensitivity to some stuff that like exotic scalars that are derivatively coupled other than axions?
Do you mean non-derivatively coupled?
Derivatively coupled, right?
Oh.
Because then you can normalize it on something not 1 over m blank, but on something.
Oh,
It's usually high dimension.
Ruled out by like the force constraints.
Right.
I mean, so if I was giving this talk a couple of years ago, I would have talked about our cavity thing to look for axions,
Right.
which was actually motivated by this Mago. So that there is looking for axions, a couple of photons and kicking them up. Yeah, and actually, there's going to be a prototype of that in October, right? Fermilab. So the answer is yes. For the photon coupling, there's something in progress. And then if you want to talk about other ultralight dark matter candidates, you could look for the dilaton-like coupling that oscillates the Bohr radius of atoms, either by coupling the S squared or the electron mass. We've done estimates, it doesn't look so great. You can actually get the pretty good sensitivity, like maybe creep just below EP bounds or the force bounds, but not by a ton.
There are no more questions. Let's thank Asher again. And he'll be around the rest of the day, and then we're also going to get dinner. So if anyone wants to get in on dinner, let me know.